Hello friends, welcome to Control System lecture. This is Dr. Nitisha Shrivastava from Indraprastha Engineering College. In this lecture, we will look at the time response of a typical, that is prototype second order system. As we know that the total order of the system usually for any particular control system is very high, but we reduce the order of the system to second order, and the mathematical analysis of a second order system is comfortable as compared to the lectures as compared to the orders of the higher order systems. Now, we will look into how we can determine the time response of a typical second order system. Now, here we will consider a second order system. This is omega n square s plus 2 zeta omega n, and it is a unity feedback system, that is h of s is equal to 1. Therefore, the closed loop response, here we can see that r of s is the input and c of s is the output. This output is fed back here. So, r of s and the difference of the signal which is fed back is required, that is why we have a summing point here. And this is the forward path transfer function. G of s is forward path transfer function. This forward path transfer function, and then a negative feedback loop whose value is 1. So, it is a unity feedback system. Therefore, the closed loop transfer function is given by the relation g of s 1 plus g of s h of s. So, our h of s is 1, therefore, it is g of s divided by 1 plus g of s h of s, where h of s is 1. And solving this closed loop transfer function, omega n square upon s square plus 2 zeta omega n s plus omega n square. So, this is the closed loop transfer function of a prototype second order system, and in the block diagram we represent it with a summing point, a forward path transfer function and a negative feedback loop. So, solving this, we are getting the transfer function, that is the closed loop transfer function of a typical second order system. We have the power of s as square, that is s square. So, it is a second order system. Now, let us see what are the characteristics of the prototype second order system, and how is the characteristics of a prototype second order system obtained? It is obtained by setting the denominator to 0. Now, this equation represents the closed loop transfer function with unity feedback. Here we have remember we have considered h of s is equal to 1. So, it is a unity feedback system. Cs by upon Rs, that is output upon input, is this transfer function. Now, setting the denominator to 0, that means this is the characteristics to determine the characteristics. So, the denominator of the equation, that is the second order transfer function, closed loop transfer function, is set to 0. S square plus 2 zeta omega n s plus omega n square is the denominator of the closed loop transfer function, and this transfer function is set equal to 0. So, it is a second order system. So, how do we find the roots? Like we have the simple algebraic formula, minus b plus or minus root of b square minus 4ac upon 2a. So, using this relation, we determine the roots of the equation. This characteristics of a prototype second order system is obtained by setting the denominator of the equation to 0. It means that this denominator equation is known as the characteristic equation. So, in control system, the characteristic equation means the denominator of a closed loop transfer function. So, when setting this to 0, we obtain the roots, and the roots are S1 and S2. We get two roots here, minus zeta omega n plus or minus j omega n root of 1 minus zeta square. So, just replacing this term omega n into root of 1 minus zeta square as omega d. So, the roots has the real part as well as the imaginary part. Now, we will look into later part why we call this as a damped frequency oscillation. We have now defining this, or we are now just naming the term omega d as a damped frequency oscillation, which is equal to the imaginary part of the root, that is omega d is equal to omega n root of 1 minus zeta square. The natural frequency of oscillation or the natural undamped frequency is omega n, and zeta is referred to as the damping ratio. So, in order to find the roots, the characteristics of a prototype second order system, we have to set the denominator part of the closed loop transfer function equal to 0 and obtain the roots. We are just defining or naming the term this omega n as the natural frequency of oscillation, omega d as the damped frequency oscillation, and zeta as the damping ratio. Now, we will look at the response of a second order system with unit step input. Now, as we know that there are standard test signals, one of them is the step function. So, we are going to apply a step function to a second order system. So, as we have already known, a closed loop second order system is omega n square upon s square plus 2 zeta omega n plus omega n square. Now, since our input is a step function, so in S domain R of s is equal to 1 upon s. So, this is R of s is equal to 1 upon s. Now, we are applying this input as clearly stated with a step input function, unit step input function. So, magnitude of the step function is 1. This is the meaning of unit step input. Therefore, applying this is a second order transfer function, and R of s is replaced by 1 upon s, and therefore, the closed loop transfer the output, that is C of s, is equal to 1 by s omega n square. Now, we have manipulated this part of the equation as it is written s square plus 2 zeta omega n s plus omega n square. To this, we have added plus zeta omega n the whole square minus zeta omega n the whole square. This is done in order to bring the transfer function into a form desirable, so that we get the response of the system. S square plus 2 zeta omega n, this part and this part is used to obtain s plus zeta omega n the whole square. So, this part of the term represents s plus zeta omega n the whole square, and we have the remaining term here omega n square and minus zeta omega n. So, this is equal to plus omega n square in the brackets 1 minus zeta omega n square, sorry, zeta square. It is omega n square 1 minus zeta square. So, therefore, just it is a we had the original equation, we have manipulated the original equation to get it into this form. So, we are just again, as we had seen in our previous value, we had denoted the imaginary part as omega n root of 1 minus zeta square as omega d. So, what will be omega d square? Omega d square will be, we can see it is omega n square plus it is 1 minus zeta square. So, that is what this term is written as omega d square. So, this is the response of a second order system when subjected to unit step input. So, applying partial fraction expansion, now we want to get it in the form so that we can get the results or we can get the final equation in the time domain, that is we are interested to obtain C of t. Applying partial fraction expansion, what happens to the equation now? We can see that C of s can now be split into a by s plus b s plus c upon s plus zeta omega n square plus omega d square, because we have an imaginary term here, and that is why now this is split into 2. When we solve this particular equation after partial fraction expansion, we obtain the value of a as 1, the value of b as minus 1 and the value of c as minus 2 zeta omega n. We have replaced the values here, we are continuing with it. We are finding out what will be the value of C of s. C of s after replacing the term 1 by s, b is minus 1. So, b minus 1 and the value of c is minus 2 zeta omega n, and that is now replaced here minus 2 zeta omega n. So, this equation of the output, that is the response of a second order system when subjected to unit step input after applying the partial fraction expansion, is obtained. Now, we are again manipulating this equation so that we can apply the inverse Laplace transform. We are taking this into the brackets. Now, this part is coming to the brackets, so this becomes positive. We are using this part for manipulation. So, both becomes positive, this term is this and this term is this. We are now adding a quantity, that is zeta omega n s plus zeta omega n square plus omega d square. We are adding and subtracting the term, we are adding and subtracting this term again for a simple manipulation, so that we can get it in the form as desired to apply the inverse Laplace transform. So, we can see here C of s is equal to 1 by s. What happens now? This s plus zeta omega n comes into the numerator and the denominator part this and this part is here. So, zeta omega n upon omega d, we are just subtracting these two quantities, we get a positive value, and this omega d is added, divided and multiplied again for manipulation. Zeta omega n upon omega d, this term. So, from this set of equation, now we have come to this part, which is now possible. Now, we can apply the Laplace transform, inverse Laplace transform rules to obtain the value of the output response in terms of C of t. So, this is the S domain, that is the Laplace domain response of a second order system when subjected to unit step input. Now, applying the inverse Laplace transform to each of the terms as given in this equation, what we get? We are applying the inverse Laplace. So, the value comes out to be 1 s plus zeta omega n s plus zeta omega n square plus omega d square. Now, what this term looks like? It is applying the inverse Laplace transform, we get an exponential term e raised to minus zeta omega n t cos omega d t plus zeta omega n upon omega d e raised to minus. right. So, this is the term which remains here, e raised to minus zeta omega n t sin omega d t. So, after applying the inverse Laplace transform, we obtain the time domain response of the value of the response of a prototype second order system when subjected to unit step input. Now, here C of t is, we are again manipulating the equation. We have now added a term, we are just replacing or just put the value of omega n root of 1 minus zeta square as omega d. So, our omega n term gets cancelled out. So, what remains of the equation, zeta upon 1 minus zeta square. Now, in this equation we are going to take 1 minus zeta square outside. So, we need to multiply the first term here with root of 1 minus zeta square, and e raised to minus zeta omega n is also taken common, and therefore, C of t is in this form. Now, here we are having a term root of 1 minus zeta square. We are in the next step using a new term root of 1 minus zeta square equal to sin phi. Now, we can understand this from here. What is 1 minus zeta square under root? If therefore, sin phi for this will be what? Sin phi is equal to root of 1 minus zeta square upon 1, and therefore, we can understand that sin phi, what will be cos phi? Cos phi will be zeta upon 1, and similarly, what will be tan phi? Tan phi is equal to, it is sin by cos. So, 1 minus zeta square upon zeta. So, whatever equation we had got here, we are using some new terms to identify it. We have clearly defined a new term phi and identified what is sin phi, what is cos phi, and what is tan phi. Replacing all those values here in place of root of 1 minus zeta square, we are replacing the quantity sin phi, and in place of zeta, we are replacing it as cos phi. So, C of t now becomes 1 minus e raised to minus zeta omega n root of 1 minus zeta square sin phi cos omega t plus cos phi sin omega dt. Instead of zeta, we have used cos phi. So, this equation is nothing but in the form of sin A cos B plus cos A sin B. So, here we are just using the relation sin A plus B. So, C of t is equal to 1 minus e raised to minus zeta omega n t, as it is the term comes down, sin omega dt plus phi. We are replacing omega d back to omega n root of 1 minus zeta square, and since tan phi is this, so we are putting back the terms phi with as root of 1 minus tan inverse root of 1 minus zeta square upon zeta. This is directly obtained from here. So, now our equation looks like this. C of t is equal to 1 minus e raised to minus zeta omega n t upon 1 minus zeta square as it is, and in place of the quantities we are using this. Now, here we can also see that we can replace phi. What is cos phi? So, phi is equal to cos inverse zeta. So, that is also possible here because we have a term phi here. We can either replace it using this value or using this value of phi. So, here the output response C of t is equal to 1 minus e raised to minus zeta omega n t root of 1 minus zeta square sin omega n. Now, we are having all the quantities in terms of omega n and zeta. After manipulation, we again back to the same form, and this equation is also the same, but instead we have used phi as cos inverse zeta. So, after obtaining the time response of a prototype second order system when subjected to unit step input, this is required for the mathematical analysis of a second order system. We obtain the time domain response, that is the C of t of a prototype second order system. Now, let us see what happens to the steady state error, and how is error determined? Error is determined by the relation E of t is the reference input R of t, whatever the reference input is given. Now, in this case it is a unit step function, therefore, R of t is simple 1, it is a unit step function. So, our R of t is 1, that is the reference input given as a unit step input, and C of t is the output response of a prototype second order system when subjected to a unit step input. So, what will the equation now become? The error E of t is R of t minus C of t. Now, we are with minus 1 minus, here we have the equation 1 minus, and when you replace here 1 minus the remaining term. So, E of t is equal to this value. And how do we obtain the steady state error? Steady state error is obtained by the relation what is the response of the system when t tends to infinity. What is the error of the system? So, here we can see applying t tends to infinity, we get the steady state error as 1. So, this is the time domain response of a response of a second order system and subjected to unit step input, and this is the value of steady state error. So, in this lecture we have derived the relation of a second order system when subjected to a unit step function, that is the magnitude of a step function having a value 1, and also seen that what would be the steady state error, that is when time reaches infinity, and we have seen that we got the value of 1. Thank you.